Hello everybody. Today we start with a new chapter in physics in ICSE Standard 10th. That is the 12th chapter from Concise Physics, Radioactivity. This is a part of the modern physics kind of the section of the chapters. So we got two chapters over here in modern physics. One is radioactivity and second is nuclear fission and fusion. So today we will start with the first part of the chapter, that is radioactivity and atomic structure. So atomic structure and radioactivity is the name of the part. The atomic structure, I don't think there is anything which is not known to you. It's very easy. We very well know that the atom is subdivided into three particles, that is protons, electrons and neutrons. The protons are positively charged particles. So we have over here, first is protons. The protons are positively charged particles having a charge equal to 1.6 into 10 raised to minus 19 coulomb, and the mass is equals to 1 AMU. And then comes the electrons. So electrons are the ones which are negatively charged particles, and they will be having a charge of minus 1.6. So this is plus or this is minus into 10 raised to minus 19 coulomb, and they have negligible mass. So this mass of this thing is negligible, and that is approximately 1 upon 1837 times that of proton. So that's why it is negligible, because it is 1837 times lighter than proton. The next one is neutron. So neutron has got its neutral, so it's neutral, and so no charge, and the mass will be as 1 AMU. So that's the mass over here. Accordingly, we have the atomic number. Atomic number is equal to Z, which is nothing but protons or electrons. So number of protons or number of electrons, because the number of protons and number of electrons in a particular atom are always the same. That's why that is Z is equal to P is equal to E. And atomic mass, we very well know that electrons have no mass, so this is in terms of A, and that is equal to protons plus neutrons, because electrons are negligible mass. So the total mass of any atom is the sum of the protons and the neutrons present in them. And the protons and neutrons are in the, so the structure goes this way, that there is the protons and neutrons inside the nucleus, and then there will be the shells which accommodates the electrons in them, and so the shells are named as K, L, M and so on. And the number of electrons which can be there in any particular shell of an atom is given by the formula 2n squared. Therefore, K will be having 2 electrons as the maximum number of electrons in the orbit, and L will be equal to 8 electrons, and M will be equal to 18 electrons, N will be equal to 32 electrons and so on. So that is what we have in this particular part. And also we know that the octet and the duplet rule. So the duplet rule is that any particular atom which has got only one orbit, they will be having only 2 electrons in the outermost orbit, and any other atom which has got more than 2 orbits will have 8 electrons in its outermost orbit. So that gives you the valence shells, that we can say the octet and the duplet rule. So that was in general about this particular atomic structure. So let's see what they have written over here in the textbook. So let's start with the structure of atom and nucleus. So first we see is the discovery of electrons by Sir J.J. Thomson and the scattering experiment of alpha particles by Rutherford and others towards the end of the 19th century led to the following structure of atom and its nucleus. So we very well know that J.J. Thomson was the first ones who discovered the electrons, and then the Rutherford experiment determined that the nucleus was the center, and there were many other to follow, which gave rise to the different the structure of the atom as a whole. So Structure of atom. An atom consists of electrons, protons and neutrons. The protons and neutrons reside inside the nucleus of the atom, which is at its center, while the electrons revolve around the nucleus in some specific orbits in which they do not radiate out energy. So whenever the atoms are going to be there, the atom will be having the nucleus at the center. The nucleus contains the protons and the neutrons, and the electrons are revolving in orbits or in the orbits around the nucleus. And when they are revolving in the orbit, they do not radiate out any energy. This is very important because if they would have radiating out the energy, then slowly and steadily the energy would have started decreasing, and what the possibility would be that the electrons would have spiraled down inside this particular nucleus and would have entered into the nucleus. But that doesn't happen. Why would that happen? Because the orbits are basically energy levels, so they have got a constant energy in it, and that's why they do not go sideways or they do not go spiral down into the nucleus, and they maintain that particular orbit. Right. Such orbits are called as stationary orbits or stationary shells. In each stationary shell, the electron has a definite energy. The number of shells in an atom depends on the total number of electrons in it. So the number of shells is different in atoms of different elements. So yeah, the number of shells is going to depend upon the number of electrons present in it, and depending upon the number of electrons there will be number of shells. So accordingly, each and every element means all the different elements will have different atomic structures, that means different number of shells in it. The maximum number of electrons in a shell can be given by the formula 2n square, where n is the number of that shell. The various shells around the nucleus are for n is equals to 1, 2, 3, 4, 5, 6, 7 are named as K, L, M, N, O, P, Q respectively. And these shells can accommodate at the most 2, 8, 18, 32, 50, 72 and 98 electrons in them. Electrons respectively. The electrons in different shells have different energy, which increases with the increase in the number n of the shells. So yeah, the electrons in different shells have different energy, and that energy keeps on increasing as the number of shells keeps on increasing. The size of an atom is determined by the radius of the shell of its outermost electrons, and it is of the order 10 raised to minus 10 meters. The electron has negative charge equal to minus 1.6 into 10 raised to minus 19 coulomb or 1 e, and its mass is me is nearly 9.1 into 10 raised to minus 31 kg, which is approximately 1 upon 1840 times, it is actually 18437 but take it 40 rounding off, times the mass of proton. So that was about the structure of the atom. Now we see the structure of the nucleus. So structure of the atom, we saw the electrons, how they are revolving, how they are placed inside the orbit, and how many can be there in that orbit. So that is what we saw about the atom as a whole. Now we are seeing the nucleus. The nucleus is at the center of atom, whose size is the order of 10 raised to minus 15 meters to 10 raised to minus 14 meters. That is 10 raised to minus 5 to 10 raised to minus 4 times the size of the atom. So you can see that the nucleus is actually very small. It is very small as compared to the atom as a whole. The atom is quite big, but the nucleus is a very small thing. You can consider this itself, the nucleus is so small, whereas the atom as such is quite big. The protons are positively charged equal to plus 1.6 into 10 raised to minus 19 coulomb or 1 plus e, and its mass MP is nearly 1.67 into 10 raised to minus 27 kg. The total number of protons in the nucleus determines the place of the atom in the periodic table and is called the atomic number. So yeah, because electrons keep on moving from one atom to another atom, that's why it is the proton which is present in the nucleus is determining the atomic number of any atom. So the atomic number is determined by the number of protons present in the nucleus of the atom. Yeah, so the total number of protons in the nucleus determines the place of the atom in the periodic table and is called the atomic number of the element of that atom. The atomic number of an element is denoted by the symbol Z. The neutron is an electrically neutral particle, charged 0, and its mass is Mn and is also nearly 1.67 into 10 to minus 27 kg. That is equal to the mass of the proton, which is equal to that of the proton. Yeah. The proton and neutron, which are the main constituents of the nucleus, are called the nucleons. Yeah, so this is the important part which I missed out, is the protons plus neutrons. The protons and neutrons which are present in the nucleus over here, because they are present in the nucleus, that's why they are called as nucleons. Okay, the subatomic particles present in the nucleus are called as the nucleons. The total mass of the nucleons is the mass the total mass of nucleons in the nucleus is called as the mass number of the element and is denoted by the symbol A. The nucleus is thus positively charged and its total charge is plus Ze. The mass of the nucleus is approximately A times the mass of protons. A times means the atomic mass number, because it is number of protons per number of neutrons. Note, the mass of electron is negligible as compared to that of the proton or of neutron. Hence, total mass of the atom can be considered to be same as the mass of its nucleus. Okay, because the electrons, however number of electrons may be there in an atom, because the net mass, or you can say the total mass of those electrons will be very less. That's the reason we are considering the mass of electrons to be negligible. Hence the atomic mass or the mass of the atom is equal to the mass number, which is nothing but the number of protons per number of neutrons present in the nucleus. That means the mass of the nucleus is considered as the mass of the atom. Thus we can define the atomic number and mass number as follows. Atomic number. The atomic number of an atom is equal to the number of protons in its nucleus, which is same as the number of electrons in the neutral atom. So yeah, if it is a neutral atom, that means there is no loss or gain of electrons. Then the number of protons will be equal to the number of electrons, and in such a case, the atomic number is the number of protons or the number of electrons present in the atom. Z is the number of protons in the nucleus of an atom. Next is mass number. The mass number of an atom is equal to the total number of nucleons. The total number of nucleons, that is the total number of protons and neutrons present in an atom, gives you the mass number. So that is the given of the number. Okay, the given of the number of protons and number of neutrons in the nucleus. So it is the number of protons and the number of neutrons in the nucleus. That is, A is equal to number of protons plus number of neutrons in the nucleus of an atom. So we can see this table. Symbol is electron is small e, charge is minus 1.6 into 10 to minus 19 coulomb, mass is 9.1 into 10 to minus 31 kg. Protons, it is plus 1.6 into 10 to minus 19 coulomb, mass is 1.67 into 10 to minus 27 kg. Neutrons is n and charge is 0, whereas the mass is 1.67 into 10 to minus 27 kg. So this was about the nucleus of the atom and the mass number and atomic number. Now we see the atomic structure or the atomic model. So an atom is electrically neutral, therefore the number of protons in the nucleus of an atom are equal to the number of electrons revolving around the nucleus of an atom. Very well, easily done. That number of protons is equal to number of electrons present in it. If Z is the atomic number and A is the mass number of the atom, then the atom consists of number of electrons as Z, number of protons as Z, and mass number, because it is A, so therefore number of neutrons will be A minus Z. So A minus Z will be the number of neutrons. The atom is specified by the symbol AXZ. So always it will be given this way, that A, that is the atomic mass, comes on the top. So if you take sodium, then it will be 23Na11, where 23 is the atomic mass number, and the 11 is the atomic number. So the atom is specified by the symbol AXZ, where X is the chemical symbol of the element. The actual size of the atom is very small, nearly 10 raised to minus 10 meters, which is invisible. But just to understand the distribution of its constituents, we can draw the model of an atom not to the scale. So this is what they just said, that we can draw it not to scale, but just to get an idea that how the electrons and the protons are placed. So the lightest atom is hydrogen, whose mass number is A is 1, and the atomic number Z is also 1. It is represented by as 1H1, and it has one proton in the nucleus and one electron in the orbit, in the K shell as shown in the figure. So it will be one proton in the nucleus over here, and in the K shell there is one electron. That is what they are given you in the diagram over here. Similar to the helium atom, as the mass number is 4 and the atomic number is Z is equals to 2, therefore represented by 4He2, and it has 2 neutrons. So it has got 2 neutrons, 2 protons and 2 electrons. 2 protons and 2 neutrons in the nucleus and 2 electrons in the K shell. Accordingly, the symbol of the diagram will be, in the nucleus there will be 2 protons and 2 neutrons, and in the K shell there will be 2 electrons. The sodium atom has atomic number 23, Z is equals to 11, and the mass number is A is 23. It will have Z is equal to 11, so there is protons, 11 protons, and A minus Z is equal to 23 minus 11 is 12 neutrons inside the nucleus, and Z11 is equal to protons distributed, electrons distributed in KLM shells. So 2 in the K shell, 8 in the L shell, and MA 1 electron. As shown in the figure, that it is represented by 23Na11. So there will be, if you draw it in this one, so you can see that over here there will be 11 protons, 12 neutrons, 2 electrons in the first shell, 1, 2, 3, 4, 5, 6, 7, 8 in the second one, and third one just 1. So this is nothing but Na. So this is Na, which is given over here like this. Note, if an atom undergoes a chemical change, there is change in the number of orbital electrons of the atom, whereas if the atom undergoes a nuclear change, there is a change in the number of nucleons inside the nucleus of an atom. So remember one thing, that whenever there is any chemical change taking place, any particular chemical change taking place, it is only the electrons which are there in the orbit which are going to move from one point to another, one atom to another atom. There would not be a single change in the nucleus of the atom. The chemical changes, chemical reactions do not undergo any nuclear change. But whenever there is a nuclear change, the orbits are going to remain as it is, but only the nucleus is going to decay or deteriorate. So the change which is going to take place in the nucleus is called as a nuclear change, whereas the change which takes place in the orbits is called as a chemical change. A nuclear change requires much higher energy of the order of for mega electron volt. Okay, it will be a few mega electron volt, which is nearly 10 raised to 6 times as compared to the energy required for a chemical change, which is of an order of few electron volts. So you can see, when an electron needs to move from here to some another atom, it is requiring a very few amount of energy. The energy which is measured to remove an electron is in the definite, or we can say the units are electron volt. It is EV, that is electron volt. This is EV. That's electron volt is the units for the energy which is used to identify the energy which is going to be required to remove an electron or to add an electron into the orbits of the atom. But if you want to have any kind of a chemical nuclear change, okay, if you need a nuclear change to take place, the energy is in terms of mega. So that is mega electron volts. Mega is 10 raised to 6. So it is 10 raised to 6 times more than what is required in a chemical change. In a nuclear reaction, the atomic number or the number of protons and the mass number or the number of protons and neutrons remains conserved. In other words, the total number of subatomic numbers of the reactants is equal to the sum of the atomic numbers of the products. Similarly, the total mass of the sum of the mass numbers of the reactants is equal to the sum of mass numbers of the product. So whenever there is a nuclear change taking place, so whenever there is a nuclear reaction where the atomic nucleus is going to change, at that time also the proton, there is no way a proton can be destroyed, okay, there is no way a neutron can be destroyed or an electron can be destroyed. Only thing is that it is getting converted into two different atoms, okay, it is getting split into two atoms. So the total mass of the reactants and the total mass of the products, or the total number of protons and the total number of neutrons present in the reactants and present in the product is going to remain the same. That's what exactly they are mentioned in the note 3, that is, in nuclear reaction, the atomic number or the number of protons and the mass number or the total number of protons and neutrons remain conserved. Okay, they are not going to change at all. They are going to remain conserved. In other words, the total sum of atomic numbers of reactants is equal to the sum of atomic numbers of the products. So, reactants and products ka mass is the same. Similarly, the total sum of mass numbers of the reactants is equal to the total number of sum of mass numbers of the product. So, atomic number and the mass number before and after the reaction is going to remain the same. So sum of the atomic numbers and the sum of the mass numbers before and after the reaction is going to remain the same even in a nuclear reaction. So no doubt we say that the radioactivity is a decay, but that decay is such that the reactants, the total number of reactants, the total mass of the reactants and the before and after is going to remain the same. Only thing is that it may split into two or more compounds, elements. We now see is one of the important things, that is isotopes. So isotopes are, so the atoms of the same element having same atomic number Z but different mass number A are called isotopes. So when any two elements, or when we have got two atoms and these two atoms are such that they have got the same number of protons and electrons, of course, so the atomic number is the same but the masses of both are different. So in such a case, what happens is that because the atomic number is the same, so the element ka naam will remain the same, because whether the atomic number is, when atomic number is 11, it is sodium, when it is 12, it becomes magnesium. So as the number changes, the element is going to change. So here the number of protons or electrons are going to remain the same, but the mass is different. That means the number of neutrons are different. In such a case, we call those elements as isotopes. So isotopes are same atomic number but different mass number. Okay, so atoms of the same element having same atomic number Z but different mass number A are called isotopes. Obviously, the isotopes have the same place in the periodic table as it depends on the atomic number Z. So, isotopes of the element, they will have the same number, same place in the periodic table. So, in the periodic table, hydrogen has got 3 isotopes, but all of them come in the first group only. If we have carbon has got two isotopes, but still it will be placed at its own place in the group number 4. So, in this way, the position of all the isotopes of one element is going to be the same. So atoms of the isotopes have the same number of protons but different number of neutrons in that nucleus. Since they have got the same number of electrons outside the nucleus, so their chemical properties are also the same. So even if hydrogen is having 3 isotopes, but all 3 of them are going to behave chemically the same way, because the valency and the number of electrons in the atom motion, everything is going to remain the same. So reactivity wise, they are just going to remain the same. That's why they behave as the same element. In nature, different isotopes of the element occur in different proportion. In most of the cases, the relative abundance of one isotope is very high as compared to the other. For example, hydrogen has got 3 isotopes, namely protium 1H1 or ordinary hydrogen, which is most abundant, deuterium 2H1 or heavy hydrogen, and tritium 3H1. Each isotope in its nucleus has one proton, that is Z is equals to 1, but protium has got no neutrons. Okay, so protium, it is this way, it is 1H1, 2H1, 3H1. So the protons are 1, 1, 1, electrons are 1, 1, 1, but the neutrons are 0, 1, 2. Got it? So this is how they are having this. So you can see it is only the change in the number of neutrons which is different, otherwise this and this are same, and this determines the chemical properties of the substance. That's why there is no change in the chemical properties of hydrogen, whether it is protium, deuterium or tritium. There is one electron outside. Okay, each isotope of this nucleus has one proton, Z is equal to 1, but protium has no neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. There is one electron outside the nucleus in the atom of each isotope. The table here gives the number of protons and neutrons in the nucleus of the isotope of hydrogen. So that is exactly what we just wrote over here. Second is carbon. Carbon has 3 isotopes, 12C6 or 13C6 and 14C6, out of which 12C6 is most abundant. Each isotope in its nucleus has 6 protons. The isotope 12C6 has 6 neutrons, and the isotope 13C6 has 7 neutrons, and isotope 14C6 has 8 neutrons inside the nucleus. The number of electrons outside the nucleus in the atom in each isotope is 6. Similarly, chlorine has 2 isotopes, 35Cl17 and 37Cl17. The relative abundance in the nature is in the ratio 3:1. So in nature, it is found that 3 parts of 35Cl and 1 part of 37Cl is present whenever you take chlorine in a particular volume. Each isotope is in the nucleus has 17 protons. The isotope 35Cl17 has 18 neutrons, and 37 has got 20 neutrons inside the nucleus. The number of electrons outside the nucleus in each isotope is 17. So note, tin has the largest number, that is 10 isotopes. The isotopes of 2 kinds. First, a stable isotope which have the number of neutrons nearly equal to the number of protons in their nucleus. So this is something important now, that why would some particular substance be radioactive? Okay, why is there a decay taking place in the atom? Okay, so it is seen over here that isotopes which are stable are such that they have a number of neutrons nearly equal to the number of protons, whereas unstable or radioactive isotopes which have number of neutrons much more than the number of protons in the nucleus, they undergo radioactive decay and are great medical and industrial use. So that is what we are studying over here, that is the radioactive part. So radioactivity is something which is about the isotopes which are unstable. So unstable isotopes, or basically any element which has got such that the number of protons, there is a vast difference between the number of protons and number of neutrons. If the number of protons and neutrons are almost same, then it is not a radioactive material, it will be a stable atom. But if the number of protons and number of neutrons has got a vast difference between the two, then we call them as they will be acting as a radioactive material. That means there will be a decay of the nucleus taking place. For example, uranium 3592 and uranium 23892. Each isotope has 92 protons inside the nucleus, but 235 has 143 neutrons, while 238 and 146 neutrons inside nucleus. In both isotopes, the number of neutrons are more than the number of protons, so both are radioisotopes. Similarly, 14C6 is a radioisotope out of 3 isotopes, 12,6, 13,6 and 14C6. The next we see is isobars. The atom of different elements having the same mass number but different atomic number. So exactly ulta of this thing, that is called as isobars. So we got next is isobars. There is same atomic mass number, different atomic number. Okay, so the atoms, of course, because the atomic numbers are different, so they are different elements altogether. So the atoms of different elements which have the same mass number A but different atomic number Z are called isobars. The atoms of isobar have the same number of nucleons in their nucleus. So that means the number of nucleons, that is sum of the protons and neutrons, is the same. Okay, sum of protons and neutrons is the same. That is the reason they are called as isobars. But different number of protons and different number of neutrons. The number of electrons outside the nucleus is always equal to the number of protons. So isobars have different number of electrons. Example, 2311Na or 2312 Mg are isobars. 2311Na contains 11 protons and 12 neutrons, whereas 11 electrons outside the nucleus, whereas 2312 Mg contains 12 protons and 11 neutrons inside the nucleus and 12 electrons outside the nucleus. The total number of protons and neutrons is 23 in each case. Similarly, 14C6 and 14N7 are isobars. 14C6 has 6 protons and 8 neutrons inside its nucleus and 6 electrons outside the nucleus, while 14N7 are 7 protons and 7 neutrons inside the nucleus and 7 electrons outside the nucleus. If the number of protons and neutrons get interchanged inside the nucleus, they are called as mirror isobars. That is in the case of Na and Mg. You can say यहाँ का जो number of protons है वो Mg का number of neutrons है और यहाँ पे number of neutrons है वो Mg का number of protons है. So if such a thing is there, then they are called as mirror isobars. So 2311 Na and 23 Mg12 are the mirror isobars. The last one is isotones. So isotones. Now isotones are atoms having different number of protons but same number of neutrons. So different number of protons but same number of neutrons. So if the number of neutrons present in the nucleus of two elements are the same, then they are called as isotones. So atoms having different number of protons but same number of neutrons, that is Z and A, but same A minus Z, are called isotones. They have different number of electrons. Example, 23 Na11 and 24 Mg11 and 12 are isotones. Each nucleus has 12 neutrons. 23 Na has 11 protons, while 24 Mg is nucleus has 12 protons. Similarly, 39K 19 and 40A are 20 and are the isotones, each having 20 neutrons in the nucleus. So this was about the structure of the atom. So that was one part of the chapter, that was the structure of the atom, telling you about the different kinds of isobars, isotones and isotopes. Now we move on to the main part of the chapter, that is radioactivity, in the next video.